This chapter is on light. Okay, light waves are transverse waves, but they're not matter waves. That means they require no medium in order to exist. So all light waves or electromagnetic waves, I'll just call them EM waves or rays, travel at this speed. So the symbol for the speed of light is 3 c, and I'll put that on the equation sheet. 3 times 10 to the 8 meters per second. Okay, now when I say light, I'm not just referring to the visible light that our eye can see. Okay, I'm talking about the whole range of different electromagnetic waves. And so visible light is just a tiny fraction of all the different kinds of electromagnetic rays that exist. Okay, so right here is what we call the EM spectrum, this picture here. And it's ordering the different kinds of electromagnetic waves from high frequency to low frequency. So you don't need to know the actual frequencies, but look how extremely high they can be. So the highest frequency electromagnetic waves are gamma rays, and then X-rays, and then UV rays they could get sunburned with. And then visible light. But visible is just a little teeny bit. So the order from low frequency to high frequency of visible light is Roy G. Biv. Okay, so that's how I remembered the colors of the rainbow. But because I'm ordering it from high frequency to low frequency on this spectrum, I do backwards the Roy G. Biv, Vib-Georg. Now it's important to realize visible light is only a tiny fraction of the whole spectrum of electromagnetic waves or light waves out there. Okay, so visible light is a part of light waves that our eye can sense. Okay, continuing on the spectrum from high to low frequency after red light is infrared, IR. And then we get microwaves. Then let's just classify all these as radio waves. TV, FM, AM. Then cosmic long waves. Okay, so you need to know the order of these categories that I circled, or am circling. Okay, so radio, microwaves, IR, visible light, in that order that I gave you, UV, X-rays, and gamma. Okay, so backwards order of those would be, as they're shown here, would be from high frequency to low frequency. Now, all these travel at the speed of light. So don't tell me that the gamma rays are traveling faster than visible light rays. No. They all travel at the same speed. And that's what I set up here. The speed of light, 3 times 10 to 8 meters per second. So if I were to ask you who has a higher frequency, green light or violet light, you would say, okay, knowing this in your head, I mean, you're going to have to learn the order of these. Knowing, so if it was between green light and violet light, you would say, oh, the higher frequency one is the one closer to the left side, the way I memorized it. So that'd be violet of the two. Who has the lower frequency, microwaves or ultraviolet waves? Microwaves or ultraviolet. Who has a lower frequency? Well, microwaves is closer to the right side. So on the spectrum, so it has lower frequency than this X-rays. Now, I'm saying, okay, let's answer this. What do light, radio, microwaves, and X-rays all have in common? They all can travel through empty space. Yeah, they can go through a vacuum. That's what an electromagnetic wave is. They all travel at the same speed. Yes, the speed of light. Through a vacuum. They all have no mass. So, yeah, there is energy. They don't have matter. So, water waves require a medium. And I wouldn't say a water wave has mass, because the water wave is actually just the energy moving through the water. So, but it's very easy for electromagnetic waves. They don't even have a medium, so how can they have a mass? So, all the above are true. What is the frequency of radio waves with a wavelength of 10 meters? Okay, wavelength, remember, is lambda. So I use the wave equation, V equals wavelength times frequency, but I know that V is really C when I'm talking about electromagnetic waves. So the frequency is C divided by the wavelength, so it's 3 e to the 8 divided by 10. So that'd be e to the 1. So that'd be 3 e to the 7 hertz. Okay, what's the frequency of light waves? So the wavelength is 6 times 10 to the 7 meters. Okay, so I'm looking for frequency, little f, lowercase f. I have this wavelength. What's the frequency? So V equals wavelength times frequency. C equals wavelength times frequency. So I'm solving for frequency. So let's rearrange the symbols. Frequency equals C divided by wavelength is equal to 3 e to the 8 divided by 6 e to the negative 7. And I get 5 times 10 to the 14th hertz. So 5 times 10 to the 14th hertz is my answer. Okay, light wave has kind of a particle nature, even though it doesn't have any mass. So light waves can be considered electromagnetic wave, yeah. But each wave consists of little tiny bundles of energy. They call it photons or quanta, like in quantum mechanics. Okay, so they're not massive. They're not atoms, but they're bundles of energy. And each bundle of energy is called a photon. That's the smallest component that we can detect for light. Okay, so our eye is even sensitive if you're really used to the dark room. Your eyes have acclimated to the darkness. If I shot a photon to your eyeball, you would see it 1 photon. Now, here's this equation for the energy of 1 photon in the light wave. The unit for energy is joules, of course. F is the frequency of the light wave that has the photon, that's composed of all those photons. That's in hertz. H is Planck's constant. Very famous constant that we'll only talk about in this particular unit, but it's all over the place in modern physics, used in a lot of equations. So Planck's constant is always going to be that 6.63 times 10 to the negative 34. That'll be on your equation sheet, of course, as will be the energy of a photon equation. Now, you should see immediately that the energy of a photon is directly proportional to the frequency of the wave that photon's part of. So the energy of each bundle of photon energy is related directly to the frequency of the wave that they're traveling in. Okay, so I could go back to my spectrum and label that on my picture. So let's go back. So I inserted that picture right here from the first page. So you can see that this is the high frequency side. This is the low frequency side. Now, from what we just showed, this would also be the low energy per photon side. This would be the high energy photon side. Now, because C equals wavelength times frequency, we can also say that frequency and wavelength are inversely proportional, as we learned before. So the high frequency side would have the short low wavelengths, and the low frequency end of the spectrum would have long wavelengths. Now let's go down here and continue where we left off. Let's use this E equals HF equation. Okay, to solve this problem, what is the energy of a photon? So I'm going to use this equation, E equals HF. So H is right here. It'll be on your equation sheet. Times the frequency is 6.5 e to the 14. Now I get 4.31 times 10 to the negative 19 joules. Now that's a little tiny amount, but that's just the energy of 1 photon. When a ray of light hits you in 1 second, you'll probably get 1 billion of those or more. And each of those energies would add up. So it can be a lot of energy, especially if you're on the left end of the spectrum. Okay, let's go to the next one. What is the energy of a single photon of red light? Wavelength is 700. Now, I kind of threw a detour on you. N stands for nano, and it's 10 to the negative 9. I will give you that on the equation sheet. So the wavelength is 700 nanometers, which would be 700 times exponent 10 to the negative 9. Okay, so now I have the wavelength. Okay, the energy equals hf. But we don't have f, we have a wavelength. So, big deal. We can get frequency, right, from the wave equation. So, the frequency equals c divided by the wavelength. So I can substitute this in or solve it right now. But I'm going to substitute it in for this, because I like to play with the letters so I don't have to write so much. So E equals hc over the wavelength. Now I plug in. So 6.63 e to the negative 34 is what h is. C is 3 e to the 8. And the wavelength is 700 e to the negative 9. And I'm getting 2.84 e to the negative 19 joules. Okay, going on to this next picture. This is a light bulb that goes on, let's say, and in all dimensions, we have waves coming out in all directions. So each of these lines, green lines, represents a wave front. Represents a peak or a crest. Each of the spaces between the middle ring between the two consecutive green rings is where the troughs are. So these are the wave fronts. These circles are called wave fronts because all the peaks line up to make that sphere. And then that sphere of peaks. But what I'm trying to show is the rays, any line coming out perpendicular to the wavefront is called a ray. And that's just an individual electromagnetic wave. So I'm going to draw the waves as rays from now on as straight lines. So whenever a ray bounces off, or it could be a wave, whenever a wave bounces off a surface that doesn't allow it to pass through, we call that reflection. So mirrors. But you're reflecting things too, light too, or else I couldn't see you. It's just we can't see our image in you because you're not really smooth like a mirror is. Okay, so but reflection is light bouncing off. Now, if it's a bumpy surface like you, the light waves won't stay together when they reflect. In a mirror, they do. But anyway, so let's be simple. Incident ray. Incident means striking. So right here is the incident ray of light. It will hit the mirror or reflective surface at the boundary right there. And what I do is I draw a perpendicular line at the point that incident ray hits. And we call that the normal. It's not the normal force. It's just a reference line. And it's always perpendicular to the surface the ray's reflecting off of. Then the ray will then reflect. We call that ray the reflected ray. Okay, so now this is the easiest law in all physics, the law of reflection. And it states that the angle of incidence has to equal the angle of reflection. Okay, I don't know why it's easier to say it than do those dumb symbols. So the angle of incidence is always measured from the normal, not from the mirror. And so too with the angle of reflection. So the angle of incidence must equal the angle of reflection. This is the angle of reflection. This is the angle of incidence. Okay, so it's super easy law. If it's a smooth surface, which I can't draw, every time a ray hits it, it will come off. And if this normal force, if it's smooth, this normal will be parallel to the other normal. And so another ray coming from the object would hit it. And notice the blue and the red reflected rays won't cross each other. So this blue one right here will stay parallel to this one no matter what the angle or incidence is. Okay, but if the surface is rough, the normals aren't going to be parallel to each other. So like right here would be this normal, and right here would be this normal. So a ray hitting here, let's say from this angle, would have to have the same angle of reflection. So it would come off like that. But the angle, the red ray would go like this. I'm trying to draw a parallel to the incoming other. And then it would reflect like that. So your eye would not see an image because look, the red and the blue reflected rays are not parallel. Your eye wouldn't figure that out. No, when light travels and hits a boundary between two different mediums, like air and water, okay, even though light travels at the speed of light, it slows down a little tiny bit when it hits into another medium, such as water from air. Okay, so when the light travels into another medium, let's look at this picture right here on the left. When light travels into a medium, at an angle besides that's not perpendicular, so at a slanted angle like with that, so it's going from air to glass, it will bend either away from the normal here or towards the normal. In this case, this ray bent towards the normal. It didn't keep on going straight. Okay, we call that refraction. When a ray enters another medium at an angle and it is bent as it enters that medium, it doesn't stay in a straight line. Okay, so we call that angle 1 the angle of incidence, like before. For this angle 2, we call that the angle of refraction. Okay, so we're looking at something like this. Here's the incident ray, then it refracts towards the normal. Whoops. Refracts towards normal. Okay. Now, this is an important case. Okay, when light enters a medium where it's slowed down, okay, here's air, this side, and here's water or glass. So here's a light ray entering. Okay, so the speed of light is slowed down a little bit when it enters the water. Speed of light is greater in the air, even though it hangs out around 3 times 10 to 8 meters a second. And here's the angle of reflection. I'm sorry, angle of incidence to the normal. Then if it's going to slow down, it's going to bend towards the normal. I don't really do that well. It's going to bend towards the normal. And the angle of refraction is going to be the ray bends toward the normal. And therefore the angle of refraction is going to be less than the angle of incidence. So here you see right there is the incident ray. And then we'll draw a normal right where it hits that surface between the glass and the air outside. And we can see that the ray therefore bends towards the normal. So we can say that here's the angle of refraction, and here's the angle of incidence right here. Okay, remember all angles are measured from the normal, the perpendicular to the boundary. Okay, now here's another point. Look, when it goes from a medium where it's moving slower to a medium where it's moving faster, the ray bends away from the normal. Okay, so this theta 2 is really for this boundary right here. That's the angle 1 for this boundary. Okay, which is really, okay, I'm just going to call it angle 2 because these two angles are the same, right? Alternate interior angles. That's getting hard to see. So that I can help that. This angle right here is equal to that angle. So, but the point is, this new angle of refraction, I don't know what to call it, is bigger than the angle of incidence. So let me just, instead of getting all confused with the numbers, let's call that angle 3, right? Let's just call that angle 3 right there. So angle of incidence for that is theta 2. And the angle of refraction for that piece right here is angle 3. What I'm trying to show you is when a ray enters a medium where it's moving faster than it was, like from the glass to the air, it will move faster in the air than in the glass. The angle of refraction, I'll just say angle of refraction, will be greater than the angle of incidence. So if it moves into a medium where it's going to be moving faster, the angle of refraction will be greater than angle of incidence. In other words, the refracted ray bends away from the normal. So it's just the opposite of what I just said, with down here moving from a medium where it can move faster to a medium where it moves slower. It bends towards the normal. But right here, when it moves from a medium where it's moving slower to a medium where it's moving faster, it'll bend away from the normal. So this table right here is showing different kinds of mediums, and each of these mediums either slows down the speed of light to some extent, except vacuums. In a vacuum, there's nothing to slow it down. So in a vacuum, the speed of light is 3 times 10 to the 8 meters per second. It really doesn't slow it down. Okay, but air, almost the same. Air, don't worry about what the number means. Air is almost like a vacuum unless you have a whole bunch of layers of air, like in our sky. Okay, but anyway, let's talk about how can we quantify how much a material will slow down light and bend it, because the more it slows it down, the more it bends it towards the normal. So here's this equation for something called the index of refraction, and it's given a symbol little n. And again, we've used little n for the number of harmonics, so don't think of that. Okay, so n is equal to the speed of light in a vacuum divided by the speed of light in the medium that has that n. Okay, so that equation will be on your equation sheet. So if you're in a vacuum, the speed of light is c is the same as the speed in the vacuum. So the v would equal c, and c over c would be 1. That's where we're getting this number up here in the top of the table. So the higher the n, this is important, the higher the index of refraction of a material, n and v are what proportional? Inversely proportional. If you decrease the v more, it makes the n go higher, right? Because this is in the denominator. Okay, so that's a very important concept. Let's use that equation. Light travels through a vacuum about 300, why did I write like that? 3e to the 8 meters per second. and through water at about 226. So that'd be 2.26 e to the 8 meters per second. I won't give you, I'll just write it like that. Calculate the index of refraction for water. Well, n equals the speed of light in the vacuum divided by the speed of light in the water. So the n of water, index of refraction of water, would be that. So it's 3 e to 8 divided by 2.26 e to the 8. E to the 8 cross out. So this would be 1.33. No unit. There's no unit on the ends. Okay, so what's the speed of light in a substance? So it's not C. If it's in a substance that's not a vacuum, that substance has index of refraction of 2.42. So N equals C divided by V. 2.42 equals 3 e to the 8. 3 times 10 to the 8 divided by V. I'm solving for V, the speed in the material. So cross multiply 2.42 V equals 3 e to the 8. So V equals 3 e to the 8 divided by 2.42, which is equal to 1.24 times 10 to the 8 meters per second. So it's gone from 3 to 1.24 times 10 to the 8. So it's significantly slowed down, but it's still going 10 to the 8. Okay, so Snell's law of refraction is simply comparing the ends of the two mediums and the angle of incidence and angle of refraction. Usually I take 1 to be the angle of incidence and 2 to be where it's going to, and that's where it's going to be refracting. So I'd probably call this rays coming from the air, so I'm going to call air index of refraction, I'm going to call that N1. It's going to the glass, I'll call that N2. This is going to be the angle of incidence, theta 1. Theta 2 is angle of refraction because it's where it's going. Now, just looking at this picture, can you tell me where is the medium slowing down the ray more, in the air or in the glass? Well, if you remember what I just taught you, if the ray bends towards the normal like it is, the speed is slower. The speed is slower in that medium. And also, I told you that. And so what if I ask you, if I continue to ask you and said, okay, who has the higher N? Okay, N and V are inversely proportional. So if you have the lower N, if you have the lower speed here, this is the higher N, this is the lower N. So you can be asked those concept questions. Okay, so angle of refraction, so that's theta 2. Angle of incidence, that's theta 1. And the substance is surrounded by water. So the substance is N2. So the water is N1. Okay? Because the substance that's doing the refracting has that angle of refraction too. So I'm going to keep consistent and call that substance. The index of refraction of that substance will be N2. Okay, so you're looking for N2. So basically, N1 sine of theta 1 equals N2 sine of theta 2. So N1 is 1.33 times sine of 50 equals n2, which I'm looking for, times sine of 40. So n2 equals 1.33 sine of 50 over sine of 40. Now, the signs don't cancel out. Don't do that. Don't go, oh, these cancel out. They don't. Okay, so I'm going to do the math. 1.33 times sine of 50. Be sure you're on degrees. Your mode is on degrees. Divide by sine of 40. I get 1.59. No unit. Okay, this next problem. Light travels through air. Okay, so I'm going to call that N1. Hits the surface of water. So I'm going to call that 1.33. I'm going to call that N2 with an instant angle. Okay, that's theta 1. What is the refracted angle? So what's theta 2? Okay, so again, N1. I don't give you very much space here. Sine theta 1 equals N2 sine of theta 2. Okay, so plug in your values. 1.0. I'm going to just make that 1.0. Okay? It's basically the same as vacuum times sine. What's sine theta 1? Sine of 30 equals N2. This is 1.33 times sine of, I don't know what that is. So let's set this up so that we leave this by himself. Okay, so I'm going to write it here. Sine of theta 2 is equal to 1 times sine of 30 over, get rid of the 1.33 by dividing both sides by it. Okay, this picture is showing a ray moving through a medium, hitting a boundary in angle. Okay, here's the normal where it hits. I'm trying to draw that. Perpendicular to the boundary. And then what happens is it bends what? Towards the normal? Yeah, towards the normal. So you should be able to, from just that picture, figure out that the end's going to be bigger in this medium. If I had drawn just what was here, no words, you would say, okay, index of refraction is bigger there because the speed is slower. How do I know it's slower? Because it bends, the refracted ray bends toward the normal. Okay, so up here would be where it's traveling from. Up here it would have, therefore, lower n, and the speed would be higher. The speed of the ray would be higher. Okay, so let me just put that faster speed here. Here, let's change the color. Faster speed. Slower speed. Now, I should know that without them having given me any information except the picture. And it all depends because the refracted ray bends toward the normal. Okay, notice right here that these diagonal lines are the wave fronts. So the distance between consecutive wave fronts is the wavelength. Okay, here's the wavelength. What has happened to the wavelength when it's gone into a slower medium? A medium where the light moves slower. It's gotten shortened. So when light slows down in a medium, the wavelength of that light gets shorter. Now, why is that? Well, it's because the frequency does not change. The frequency stays constant. Jeez. And because the frequency stays constant, using the wave equation, if frequency stays constant, the speed and the wavelength are directly proportional, right? So if the medium is going to slow down the speed, the wavelength is going to get shorter. In the medium where the speed's higher, the wavelength will be longer, as this is showing right here. So I summarized all those concepts in this table right there. So we have a special case that happens when light enters a lower end medium. So, remember that light bends away from the normal when it enters a lower end medium. The bigger the angle of incidence gets, the bigger this angle of incidence gets, the more the refracted ray bends away from the normal. Eventually, the refracted ray is going to go, as you can see here, it's going to refract right along the boundary. When that incident angle gets to a critical angle, that's when that happens. So you can see this critical angle is the angle of incidence. We call it the critical angle when the angle of refraction is 90 degrees. So you can see that right there. So when the light's going through a higher end medium to a lower end medium, and the angle of incidence is the critical angle, that angle of refraction will be 90. Now what's weird is if you exceed the critical angle, let's say that was the critical angle. If the angle of incidence exceeds the critical angle, like this ray is doing right there in this picture, none of it will go out this transparent boundary. It won't go through. It'll just reflect back on itself. We call that total internal reflection. Total internal reflection. I just call it, I abbreviate it TIR. No light will refract. You get 100% reflection. So the N of diamond is 2.42. Okay, so I'm going to call that N1 because I'm doing a critical angle. The critical angle, say to C, is an angle of incidence. So the diamond is N1. Now, what's the value of refracted? I have to say in air, when it's in air. So the critical angle will be different if it's in a different medium, like if the diamond was underwater, which we'll do in the next problem. So we're going to do sine of theta 1 times n1 equals n2 sine of theta 2. Okay, so 2.42 is what the end of diamond is. The end of air, which is N2, is 1, just like a vacuum. I mean, you should know that. Okay, so 2.42 times sine of, I'm looking for that critical angle, equals, now that's where people get confused. What is angle of refraction when you're on the critical angle? It's 90 degrees. And sine of 90 is 1. So that makes life easy. It's always going to be like that. No, this might be different, and 2 might be different, so that this number might not be 1. Okay, so sine of theta c, critical angle is sine of the critical angle is 1 divided by 2.42. So the critical angle is get rid of the sine by inverse sining the other side. And that equals 24.4 degrees. For this problem, refractive index of the glass, okay, so it starts out in the air, but really I'm looking at the glass. So this would be the critical angle if the angle of refraction is 90 degrees, which it shows it to be in the problem. So critical angle is the angle of incidence. So the angle of refraction is 90 degrees. So I just use, again, n1 sine of theta 1 equals n2 sine of theta 2. And this is air, so n2 equals 1. So we're looking for the n1. We're looking for n1. The index of refraction of glass. They call it the refractive index. Same thing. Okay, so n1 times sine of 33.5 equals n2, 1 times sine of 90. So this all equals 1 on this side, divided by a sine of 33.5. And that will give me what my n1 is. And I get 1.81, which is that choice. So this first part is just using, I'll use that part. The air will be N1 because that's where the ray's coming from, at least for the first part. And then the glass will be N2. Let's see, pick the right angle. The angle of incidence would be from the normal, so don't pick this one right here. Don't pick that one. And the angle of refraction would be right here from the normal. You always take it from the normal. Okay, so I use Snell's law. I'm trying to find what N2 is, see if it's 1.61. So N1 is air. N1 is 1 for air. Sine of 47 equals N2 times sine of angle refraction 27. So rearrange this. N2 equals sine of 47 divided by sine of 27. So I get 1.61 for N2, which is what I just proved that it was what they thought it was. Okay, let's do part 2. So I want to know right here is how the ray is going to behave. How this ray is going to behave. Now, I've just switched what N1 and N2 are. Okay, so the ray is coming from, I call this N1 now, and I'll change the blue so you won't get as confused. So N1, we just found to be 1.61. Air's N is 1. Now, this is the critical angle. I'm sorry, that's the angle. No. Be careful. Okay, the angle from the normal, notice the normal is this guy. The normal is this guy right here because it's perpendicular to that boundary right there where the ray hits. Okay, so I'm going to just repeat what I just did with Snell's law. N1 sine of theta 1 equals N2 sine of theta 2. But I switched around the ends, which I just like to do. So 1.61 times sine. Okay, now this isn't going to get me anywhere. I want to know if this angle of incidence is the critical angle. Okay, so let's solve for the critical angle. Okay, let's pretend that is the critical angle and solve for it. See if it's 63. Okay, so N1 sine of the critical angle is 1, that's the air, times sine. Well, if this is the critical angle, what would have to be theta 2? What would have to be the angle of refraction? Well, it'd have to be 90 degrees by definition. This is always 90 degrees if on this side you're talking about the critical angle. So this all comes out to 1. And sine of theta c would equal 1 over 1.61. Okay, so theta c, critical angle is sine, inverse sine of 1 over 1.61. So 1 divided by 1.61, then inverse sine that. I'm getting 38.4. Now, this is where you think. 38.4. How's that compared to 63? Well, wow, 63 is 63 right here. The angle of incidence is, the actual angle of incidence is much greater than the critical angle. So when the angle of incidence is greater than the critical angle, you got TIR. So that ray will reflect at 63 degrees totally. Okay, so I can predict that yes, total reflection will occur, and there will be no refracted angle. In fact, if you tried to do Snell's law to solve for it, let's just show you. If you tried with these values up here with 63, so let's do it. So n1 sine of theta 1 equals n2 sine of theta 2. And let's just see what happens. We'll put 1.61 here times sine of 63 equals n2 1 times sine of theta 2. Okay, I'm going to solve for theta 2. And this is what, let me just bear with me. So, we're solving for this. So sine of theta 2 equals 1.61 times sine of 63, which is 1.43. So theta 2 is inverse sine of 1.43. Now when I plug that into my calculator, I get an error message. I didn't do anything wrong. When that happens, that means you don't get an angle of refraction. There's an error because no angle of refraction occurs. So, I mean, you could do it that way if you want that strategy. And if you get an error, you know that you're beyond the critical angle with that 63 degrees. So I'd rather find what the critical angle was and see that the 63, so 38 is like right here somewhere. So 63 is well beyond 38. So you're not going to get any refraction. I like the blue way better. Okay, well, that's the end of this kind of short chapter.